Okay, so we just heard that there was kind of an important difference between DC current, direct current, meaning that the current always flows in the same direction, versus alternating current. The current sometimes, half the time flows this way, half the time flows this way. Essentially the current would look like a sine wave, where you would characterize sometimes it's positive, sometimes it's negative. And so we can have these kind of two different types of electric power. We can have DC or AC electric power. And so in the early days of kind of commercial electricity, they were trying to figure out, well, which one of these is better for transmitting electric power. DC is generated at lower voltages, so if we want to transmit high amounts of power at low voltages, what must be true? High power, low voltage, high current. High current means,
high resistance.
well, it's not changing the resistance, but if we have the wire has a resistance and we have a high current flowing through that wire, we have high power losses going through that wire. So they realized that essentially if we were going to use DC electricity, we had to have the generator stations very close to where it was being supplied, because the long lengths of wire would have some resistance. So we had to think about how can we change the voltage. And AC power makes it really easy to change the voltage. Now all of you in your pocket have something that can change voltage. So this right here, exactly. So the battery in this is only producing probably 1.7 volts, maybe whatever twice that is, depending on how the batteries are arranged. But then inside of it, there's circuits that are operating at 3.3 volts, there's circuits that are operating at 5 volts, there's circuits that are operating at 1.2 volts. And then you plug it into the wall, and you're plugging this little thing into a wall that has 120 volts. And in order to do that, you need what? You need that little adapter plug, the little wall wart. Essentially with the advent of semiconductors, we were able to figure out how to build circuits, especially like circuits that could convert between AC and DC, and then can convert between different voltages in DC.
So in the phone, it's a DC.
Yeah, because all batteries are DC. All batteries and all photovoltaic panels are DC. So we'll see that in a little bit. So, but that becomes this kind of problem, is that batteries and PV panels are DC, but rotating generators and motors, and to some extent light bulbs, don't really care.
So we have to have an inverter to change from, or like.
So yeah, essentially, that in order to go from AC to DC, you need a rectifier, something to take the negative portion of the voltage and turn it into a positive voltage. We'll see that in a little bit. And then to convert DC to AC, you need an inverter, which we'll also see in a little bit. Okay, so different types of electric machines. A static, essentially, it's not really an electric machine, but it's kind of in the same category, is a transformer. And I don't mean like an Optimus Prime kind, I just mean a bunch of coiled wires, and we'll see in just a second. And then don't worry about, essentially just worry about these headers. So transformers don't actually physically move, but we call them machines anyways. And then there's generators and motors are just opposites of each other. So one converts mechanical energy to electric energy. Is that a generator or a motor? Mechanical energy to electric energy.
Generator.
Is a generator. And then a motor converts electric energy to mechanical energy. And the operating principles are pretty much the same. We'll see that in just a second. And so we can either do that with AC electricity, and there's two different types, a synchronous or an asynchronous induction motor. And then there's DC motors. So DC motors are either brushed or brushless. If you recently bought a power drill, like a cordless power drill from Home Depot, or Lowe's, or wherever your favorite place to buy your tools are. Do you think that's operating off of AC or DC power? It's a corded one, DC. Or cordless, DC, because it's running off of a battery. And so, pretty much up until 5 years ago or so, pretty much all little motors were brushed motors. But if you go by the top of the line ones now, they're using top of the line lithium ion batteries, and then they're also brushless motors, and I'll show you in a second why that's kind of an important thing. But yeah, again, don't worry about the details of that too much. But just to kind of show you what a typical synchronous AC motor, the reason it's called synchronous is that if the AC electricity is at 60 hertz, that means that this thing is rotating synchronous with 60 hertz. It might not be rotating 60 times a second, but it'll be rotating in some multiple of that. It's actually a really nice video, but or a little animation. There we go. Okay. Oh. Microsoft PowerPoint is not responding. Restart the program. But while that's restarting, yeah. Okay, let's try this again.
It's not 57 degrees outside right now.
So that's since the beginning of the year.
Yeah, just always said the same thing.
Yeah.
Okay, let's. Okay, well so we have essentially 3 different coils of wire. One coil of wire is kind of coming in and then going through there and around behind the board. So we have one kind of coil of wire that's red. We have one coil of wire that's green. So it's essentially a coil wire that's going this way. And then another coil wire that's blue going this way. Now if I take a coil of wire, so if a coil of wire like this, and I spin a magnet inside of it like this. So in this case, the magnetic field's going this way. In this case, the magnetic field that's passing through perpendicular to my coil is 0. And then when I flip it around, or when I flip it this way, now it's going north-south the other way. And so I have a changing magnetic flux through my coil. But notice that when it's kind of perfectly unaligned this way, it's kind of not quite optimally aligned, but slightly off the line of this way. And so when we're rotating this, we actually have 3 different circuits that we're producing with 3 different wires. And so this was the Excel sheet that you worked on probably the last part of your homework, where you have 3 different voltages that are all oscillating. Sometimes they're negative, sometimes they're positive, because that magnet inside of it is spinning. Sometimes it's north-south, sometimes it's south-north, and producing these oscillations. Okay, and now these oscillations are at 60 hertz, if it's a synchronous motor connected to the US electric grid. If it's a synchronous motor connected to parts of the European electric grid, it might be up at 50 hertz. So typically it's either 50 or 60 hertz. So if we have a DC motor, that means that the current's always only flowing the same way. Well, actually, there's previous. So this, I just kind of described it as a AC synchronous generator, because I said that the moving magnet was producing a voltage in these coils, right? Now imagine if we were applying a voltage to this coil. I apply a voltage to a coil of wire. What happens inside of that coil of wire? Second rule that we talked about last class. This is the first thing, that diagram we just had up. So if we have a current flowing through a wire, what happens? We create a magnetic field. And if we coil that wire up, we just create a concentrated magnetic field. And so if I have this coil of wire, this red coil of wire, and I apply a magnetic field apply an electric current to it, I'm going to produce a magnetic field. And if that magnetic field, let's say, is So actually, let's say that this way, that the north, so I put a current through these this coil of wires, and let's say that creates a magnetic field with the north pole up here and the south pole down here. This north pole is going to want to apply a magnetic force against this north pole, which is going to cause this north pole to want to move away from that, which is going to cause this magnet to spin. So we can essentially use those three rules to design different generators, different motors. So here we have a DC generator or motor where our voltage must always be positive. So how do we create a changing magnetic field that must always be positive? And what we can do is we can essentially create little switches that, imagine if, let's say B is at 0 volts and A is at 5 volts. So little 5-volt DC motor. If I'm kind of, let's say, if I'm on this wire, let's say I'm right here, and I'm kind of looking this way along the wire, is the voltage increasing from here to here, or is it decreasing? So this is at 0 volts, this is at 5 volts. Is the voltage from here to here through that yellow wire increasing or decreasing?
Decreasing.
I essentially said this is 0 volts, so this is 0 volts. This is 5 volts, this is 5 volts. So from here to here is increasing. Sorry if that was confusing. But now, let's take this entire yellow wire and start rotating it. Okay, so this yellow wire here, it's rotating, kind of rotating like this. But now, when it rotates just a little bit further, the two ends of the yellow wire jump contacts. So now this yellow wire is connected to this side of the circuit, and this yellow wire is connected to this side of the circuit.
Is there ever a point where they're like...
For a split second, yeah. But now, so this yellow wire used to be kind of looking uphill from 0 to 5 volts. Now, when it jumps like this part of this same end of the wire is now looking downhill from 5 volts to 0. See that? So if this wire is rotating, essentially, think about this as gravity. If I'm just like on this and it's moving around, and now if I'm here, I'm kind of looking uphill, and I'm still looking uphill, and I'm still looking uphill, and then all of a sudden I jump over here, and now I'm at 5. So all of a sudden I jump from 0 to 5 volts, and the other end of my wire is at 0 volts now. So all of a sudden I jump to the top. And so that's how you can create an alternating current, or an alternating magnetic field with a constant current. You just kind of flip-flop which way your current is looking.
Is it always spinning in the same direction?
Yeah, it always has to spin in the same direction. Well, unless you put it in reverse, then it'll spin the other way. And yeah, it actually doesn't really. Once it starts moving, it'll stay moving in that same direction. Then we can see, like in this way, the magnetic field is like kind of maximum, that cosine term, and then in this case, our magnetic field is at a minimum. So this is the magnetic flux. So with that changing magnetic flux, we can create either a generator or a motor. And so what does this look like kind of a little bit more physically? So we have this rotating, so we have permanent magnets on the outside and a rotating coil on the inside, and we can kind of see our shoes moving around, and then these are our brushes, which kind of jump on the opposite sides of those.
What happens when it turns yellow?
It's essentially in that split second that you were just talking about, where essentially it's missing both of the brushes are missing those shoes.
Okay.
But it's such a short period, and there's enough momentum, enough rotational inertia that it can kind of skip over that little bit. But the problem is if it just happens to be right in that yellow point, and that's when you're trying to start your motor.
Or stop it, or that's when you stop it.
Or when you stop it, but more when you start it. you have a problem because essentially you can't start the motor. And so this is why on some like really old DC motors and kind of little toy DC motors, and actually your DC motor that you invented last class, you kind of had to give it a little kick first. Because you needed to get it a little bit of momentum going in order to get it to really start moving. Now you can imagine that this is a moving part that kind of has an electrical connection, that these brushes here, so these little pads here can actually also be like wire brushes that kind of form an electrical connection, that electrical connection can sometimes wear out, can mechanically break down. And this is why we kind of moved from brushed DC motors to brushless DC motors. And so a brushless DC motor looks like this, very complicated, and you need a bunch of electrical circuitry in order to kind of constantly switch these different magnets on and off. Now there's two different parts of a motor. There's the rotor and the stator. So one of them is rotating, one of them is staying still. Which one do you think is which?
The one that's rotating is a rotor.
The rotor is the one that rotates. Now, in this case, the rotor has the permanent magnets, and the stator has the stationary, has the electromagnet. But you notice in the previous slide, sometimes the permanent magnet is on the outside, so the stator is the magnet, and the rotor is the coils. So it doesn't, you can kind of design different types of motors. We're not going to go very much into how to design motors. Take a course in E&M and then eventually in motors if that's something you care about. But transformers, why do we use AC electricity instead of DC electricity? So we know that if we have a voltage and a wire, that wire has some resistance, that will create a current through this wire. So the current is equal to V equals IR, so I equals V over R. This coil has some resistance, R, RP. So, and if I drew this as my power source, is this providing AC current or DC current? DC. This is essentially the schematic of a battery. We assume that it's DC. This is the positive terminal, this is the negative terminal. Now, current flowing through a coil of wire produces a magnetic field that is equal to the number of coils, number of turns in that coil, NP. Let's call this the primary coil, so NP, the number of primary coil turns, times mu naught, the current through that coil, divided by the radius of that coil. So this is the same equation we went through last class.
It says radius, it's just the the radius.
It's
not
yeah, like from here to here.
Okay, it's not like the distance between the wires.
No, it's just the radius of the coil. Now, let's say we have another coil on the outside here. And so here I have a voltmeter. So I have a big coil, and I have a constant magnetic field. The constant magnetic field, because my current is constant, my radius is constant, the number of turns is constant, and mu naught is a constant by definition. And so here I just happen to have a blue coil that has a permanent magnetic field going through, or a static magnetic field going through it. Nothing happens. DC electricity is such a bum. Now let's look at AC. So let's say that this voltage source is a sine wave with frequency omega and voltage amplitude Vp. So my current is flipping directions because it's essentially, my current is the derivative of my voltage. So now my magnetic field, my equation is still exactly the same, but I'm saying that now my current is a sine wave. So my current is sometimes positive, sometimes negative, which means that magnetic field is sometimes positive and sometimes negative. Now, because I have an alternating magnetic field inside of my big coil, I can say that the voltage on the ends of my big coil, this is the third rule, is essentially proportional to the number of turns in my secondary coil, the blue one, times the derivative of the, like essentially the change in flux of the change in the magnetic flux. Now here I said that the voltage is equal to, essentially the change in flux, the number, yeah, so this is the magnetic field, and we can essentially multiply it by the area to get the magnetic flux. I'm going to hand wave through this a little bit because it's not important and it's just too deep for this class. But we can essentially do some math that says the voltage in the primary coil, the voltage in the secondary coil is equal to the voltage in the primary coil times the ratio of the number of turns in each one of these coils. So we can essentially see NP over NS equals VP over VS. So if the secondary coil has more turns than the primary coil, what happens? Secondary coil has more turns than the primary. NS is greater than NP.
Voltage goes up.
The voltage will go up. Right? So if the voltage goes up, so actually I think that's, so what this is called a transformer. So this is essentially a simpler way of thinking about a transformer, where we have some sort of iron core to kind of help channel this magnetic flux. And we have this relationship. So NP over NS equals VP over VS. And if we have more coils if we have less coils on the secondary, the voltage will go down. If we have more coils on the secondary, the voltage will go up. Now we have a device that allows us to adjust the voltage in a circuit. So if our generator is producing a low voltage but a lot of power, so it means a lot of current, so we have a very, let's say that this is the low voltage side, the generator side, so low voltage, high current, and let's say that there's more turns over here, so now I have a higher voltage but the same amount of power flowing through, assuming that my efficiency is 100%. It's going to be a little bit less. But assuming my efficiency is pretty much 100%, I now have a higher voltage. What is that going to do to my current? Decrease the current. And so now I have a way to decrease my current flowing through my long transmission lines. And that's why we use AC electricity in our power grid. So how do we convert between AC and DC electricity? This is only something that we've been able to do in the last 60 to 80 years. Anything older than 20 is infinitely old for all of you, right? Yeah, so when my dad went back to school to learn this kind of stuff, it was kind of in its early stages, and now it's kind of common knowledge. Here we have an asynchronous AC generator. Don't worry about it, but it's a generator that doesn't turn at a fixed frequency. What sort of rotating power generation? A wind turbine, right? We can't control what the wind speed is, so we can't necessarily control what speed our wind turbine is spinning at. And so we end up with some sine wave of output, but we don't know what frequency it is. So what we do is we use this rectifier. Essentially, it's a series of circuits that if we have an oscillating current, it just kind of takes the negative part and turns that into a bump on the positive part by essentially doing that, like flipping it upside down thing, just by turning two different switches on and off. It's pretty cool because it's an entirely passive thing. You don't actually need to be turning switches on and off, but it's a bunch of check valves. These are diodes, if you know anything about circuits. So we can take an AC waveform, turn it into an always positive waveform, And then if we put a capacitor around that, we can essentially take the average of that. And so now we have this average of this bumpy waveform, and we can turn this always positive signal back into an AC waveform. How do we do that? We can do essentially the opposite of what this is doing. So we can take this always positive waveform here, that's kind of buffered by these capacitors, and just flip it back and forth by these two switches here. And so that essentially creates a square wave. Now that's not a very nice looking, we expect our AC electricity to be a nice sine wave, not a square wave. So the square wave could actually cause a bunch of problems. So we want it to look a little bit nicer, so we add a couple more switches to kind of make it step along the way, or even more to make it step more along the way. And so if you are buying an inverter for your car so that you can go camping and power your whatever, you probably want to, especially if you're empowering an audio system in your car, you probably want a pure sine wave inverter. Otherwise what might happen? Essentially you'll end up with noise. And especially noise, not just like white noise, but you'll end up with like noise probably around like a 60 hertz kind of hum. You ever notice in an audio system, especially an analog audio system, you'll hear like anyone have their guitar tuner on them? I bet if you did and you kind of put it up to wherever that hum was coming from and you converted whatever tune it said it was to hertz, it would say that that's a 60 hertz hum. So that hum is a 60 hertz hum because there's some, do you have a guitar tuner on your phone?
I do, but it's not.
Can you convert it to hertz, or does it only give you the musical note?
Just the note. It's also not loud enough to.
Yeah.
Unless you can.
Okay, so we some of them have like a spectrum analyzer too mode, but don't worry about it. So we have, let's just kind of going back to, let's say that this is the generator producing our electricity, typically look like this, and we essentially, over very long distances, those big power lines that you see going down the highway, notice how there's always 3 wires? These are the 3 wires that you analyzed in that last problem of your homework. Sometimes there's a 4th wire, which is kind of like the ground or the lightning arrestor wire. And then, so we know that power is voltage times current, and we know that voltage is current times resistance, V equals IR. And so if R is constant and a real number, R can be an imaginary number, which gets really complicated essentially. That means we have capacitance or inductance. But in this class, we'll only assume that R is a real number. Then both of these sine waves are kind of synchronized. Both the current and the voltage are together. And so voltage times current is power. So that means that when these two are multiplied, there's 0. So the power is 0. And then when we multiply them together, the peaks together, we get V times I, which gives us the power. But that's the instantaneous power. So sometimes the power is the peaks, and sometimes the power is 0. What about, does the power turn negative here? No, because a negative times a negative is a positive. And so here, this power and this power are exactly the same positive number. And so our power, you should have seen this in your homework, goes from very positive to very positive, even though the voltage and current go negative. And so what you wanted to do in your homework was this. So you essentially derived this calculation in your homework. That essentially the average voltage and the average current is the peak divided by the square root of 2. Everyone settle on that in your homework?